In the vast expanse of the universe, where gravity reigns supreme and light itself can be trapped, lies a phenomenon so powerful it could redefine our understanding of physics. Could the key to humanity's greatest scientific puzzle be hiding inside something we've feared and admired for over a century? A force so intense it bends time, warps space, and now may accelerate particles with more power than anything we've ever built. And unlike anything made on Earth, it already exists, billions of times over, just waiting for us to listen. These are not science fiction fantasies. They are real, spinning, seething monsters scattered across galaxies, and they might just be doing the universe's deepest experiments for us. For decades, physicists have tried to unlock the secrets of dark matter, a mysterious, invisible substance that makes up about 85% of all matter in the cosmos. We can't see it, we can't touch it, but we know it's there because of its immense gravitational pull on galaxies. Earth's most powerful machine, CERN's Large Hadron Collider, has brought us tantalizing glimpses of the subatomic world. But progress has slowed. Even after the Higgs boson was discovered, many expected dark matter would follow. It hasn't. Next-gen colliders could cost up to $30 billion, and recent funding cuts have put many projects in limbo. Entire proposals for future colliders, like the Future Circular Collider in Europe or the Circular Electron-Positron Collider in China, now hang in the balance. Meanwhile, the public appetite for multi-billion-dollar science infrastructure has weakened in a world balancing climate emergencies, pandemics, and geopolitical instability. With terrestrial options shrinking, scientists are now looking to the stars, and specifically to black holes, as the universe's own particle smashers. And in doing so, they may be laying the foundation for a new era of cosmic observation, where physics and astronomy become inseparable. On June 3, 2025, a provocative new study was published in Physical Review Letters. Conducted by a collaboration of astrophysicists from Johns Hopkins University and the University of Oxford, the paper outlines a revolutionary concept, using black holes as natural cosmic-scale particle accelerators. The lead researchers, Professor Joseph Silk and Dr. Andrew Mummery, suggest that the violent high-energy environments around supermassive black holes, those lurking at the centers of galaxies, could generate particle collisions at energies far beyond anything human engineers can achieve. These black holes, some with masses millions or even billions of times greater than the Sun, spin at near-light speeds. Surrounding them is a maelstrom of matter, an accretion disk comprised of gas, dust and stars pulled in by the black hole's gravitational grip. As particles spiral inward toward the event horizon, their speeds increase dramatically. According to the study, this inward spiral creates conditions ripe for particle collisions at unimaginable energies. Dr. Mummery explains, particles plunging towards black holes can reach similarly high speeds to those in colliders, and if they collide near to the black hole's event horizon, they can reach extremely high energies. These aren't mere theoretical speculations, they're grounded in known physics and observed astrophysical phenomena. And the idea isn't entirely new, it builds on a foundation of past work, exploring the so-called Penrose process and the Barnardos-Silk-West mechanism, both of which describe how rotating black holes can, under the right circumstances, boost particles to extreme velocities. But this is the first time the theory has been fully framed as a replacement for Earth-based colliders. The paper details the physics behind these accelerators. As matter falls into the spinning black hole, it's subjected to intense magnetic fields and extreme gravitational gradients. These two forces act together, accelerating particles in the accretion disk to relativistic speeds, meaning speeds close to the speed of light. Occasionally, these accelerated particles don't get swallowed, but instead get flung outward in narrow, high-energy jets that extend across light years. These jets, observed by radio and X-ray telescopes for decades, may carry the signature of exotic particles, perhaps even those related to dark matter. While Earth-based colliders work in tightly controlled environments, black holes operate on a chaotic, enormous scale, introducing complexities, but also possibilities, that Earth simply can't replicate. There's also the prospect of observing these collisions indirectly, by detecting the particles that escape. The twist? These high-energy collisions may already be sending messengers across the cosmos. Neutrinos, extremely light, ghost-like particles, can pass through entire planets without leaving a trace. But at ultra-high energies, they become detectable, albeit rarely. That's where Earth's detectors come in. Facilities like the Ice Cube Neutrino Observatory, buried deep within the Antarctic ice, and the KM3 NET telescope in the depths of the Mediterranean Sea are designed to capture these elusive signals. They act like enormous three-dimensional cameras, waiting for flashes of light triggered by a neutrino passing through a molecule of water or ice. If even a few particles from a black hole collision are detected, it could open a new window into the dark universe. Professor Silk elaborates. If supermassive black holes can generate these particles by high-energy proton collisions, then we might get a signal on Earth, some really high-energy particle passing rapidly through our detectors. The prospect is mind-bending. Using telescopes and detectors on Earth to study events happening millions of light-years away, in some of the most extreme environments in existence. And if dark matter is involved, if even one signature matches predicted models, it could represent the most profound shift in physics since the discovery of the Higgs boson. What's more, these findings could hint at previously undetectable physics, forces and interactions not predicted by the standard model. We might even detect signatures of particles that interact only via gravity, or through unknown quantum forces, providing the first experimental evidence for long-theorized ideas. This concept isn't just about saving money on particle colliders. It's about rethinking how we explore fundamental physics. Instead of confining our experiments to underground tunnels and magnets, we could study naturally occurring cosmic labs, black holes, neutron stars, and galactic cores. It's a shift from building ever larger machines to developing ever smarter ways to observe the universe. It could even change how we teach physics. Rather than siloing astrophysics and particle physics into separate realms, this idea bridges both, unifying the cosmic and the quantum. High-energy astrophysics could become a practical frontier in particle research, something that previously felt abstract and disconnected. The implications stretch beyond dark matter. These collisions could help us understand supersymmetry, quantum gravity, or even the conditions present just moments after the Big Bang. They could tell us whether space and time are truly smooth, or whether they break down at the smallest scales. They might even offer insight into the behavior of extra dimensions, if such things exist. And importantly, this strategy levels the playing field. Countries or institutions without the infrastructure or budget to build a collider could still contribute by monitoring neutrino activity, studying black hole jets, or simulating particle behavior near event horizons. Science becomes more global, more collaborative, and, paradoxically, more grounded, even as it reaches into space. As this new vision of cosmic laboratory physics gains traction, we may see a future where large observatories, space telescopes, and high-altitude neutrino detectors form the core of humanity's next great scientific adventure. And the more we look up, the more we may realize that the answers have been raining down on us all along. We are on the brink of a cosmic revelation. For over a century, black holes have represented mystery and danger, regions of space where physics breaks down. But now they may be our most powerful allies in understanding the unseen universe. If they truly serve as nature's ultimate colliders, then the next generation of discovery won't be built. It will be found. This is the new frontier, not miles underground, but millions of light years above. Subscribe and join us on this journey into the unknown as we peer into the hearts of galaxies to decode the very particles that shape reality itself. The secrets of the universe are not locked away. They're accelerating toward us at light speed. The universe has already begun the experiment. All we have to do now is pay attention,